Welcome to Chapter 9, Sampling Distributions, our first section of inference. Yay, we're done with probability, so let's get started. Statistical inference. It's making a prediction about the population based on the measurements of a sample. A parameter is a number that describes the population. As far as we're usually concerned, we don't actually know the value of our parameters. If we did, we wouldn't need this class, and then we would be predicting nothing. For example, if I wanted to know the mean weight of fish, I couldn't find that. The population of fish is so large, and I could never possibly collect all the fish to figure out what exactly the mean value of their weight is. So a parameter talks about the population as a whole. A statistic is a number that can be computed from the sample data. We often use the statistic to estimate an unknown parameter. We look at the sample, which gives us the statistic to predict what the parameter or what the population really is. So how I think of it is population deals with parameter, so they both start with P's, and then sample and statistic both start with S's, so that's how I know if something's a sample, I'm talking about statistic. Notation for parameters, we usually use Greek letters like mu and sigma, and for population proportions we use P, or also rho. P is also known as rho. For statistics, we use Roman letters like X bar and S, and for sample proportion, we use P hat. So yes, we are now introducing P hat. So if we are talking about a population, think of Greek letters, so mu, sigma, and P. Remember, mu is for a mean, sigma is for standard deviation, and then P is for a proportion. Remember, proportions are usually talking about percentages. And then if I have a statistic, I use X bar, S, and then P hat. I always think of statistics having a funny symbol, so like the bar and then the hat. Okay, so here we have to decide if they are talking about a parameter or a statistic, what the number represents. So the average height of all adult males, human males, is 70 inches. Because it says all, we're going to say that it's the population. Now, since we're dealing with the population and population starts with a P, it's going to be a parameter. So for parameter, average or mean is going to be mu, and mu is equal to 70 inches for this one. For the next one, median income of a sample of 1,000 adults in Texas is $25,000. So because they told us it's a sample, so we're dealing at sample starts with S, statistic starts with S, we're dealing with a statistic. Now there's no symbol for median, so I'm not going to write anything. I'm going to say that 25,000 is the median. 52%, we're dealing with a proportion here, of all Orlando phone numbers are unlisted. All means population. Population starts with a P, so it's going to be a parameter. And for a parameter, we have a Greek letter, which is going to just be rho or P equals 52%. And the last one, 52 out of 100, or another, again, 52%, randomly selected Orlando phone numbers were not listed. 52 out of 100, 100 means that it was a sample because there's a lot more than 100 phone numbers in Orlando. So I'm going to say that's P hat, and this is a statistic. This is part of your quiz. You're going to have to decide if something's a parameter or statistic, and remember that all the notation for it. So we have X bar, S, and P hat for statistics. And then for our parameters or population, we have mu, sigma, and just P or rho. Sampling variability, the notion that our sample statistics will not be the same for every sample. Think about it. If I take an SRS, a simple random sample of 100 women who live in Orlando, and I find their average height, X bar, then I take another SRS of 100 women from the same population, would I get the same number? No, because I have two separate selections of 100 women. So the means of 100 women for two different samples could be different. Like I said, they could be different. Will they always be different? Maybe, maybe not. Maybe for some odd reason we take a sample of 100 women and we get the same height for both samples. It could be possible. We can account for this by taking many samples. So like I said, we're not always going to get the same mean. So the best way to figure out what the parameter of the heights of women in Orlando is just taking a whole bunch of samples. We take a large number of samples from the same population. We calculate the mean or X bar of a sample proportion, p hat for each sample, and then we make a histogram of these values of X bar or p hat and examine it for center, shape, and spread. Do you remember this? This is from back in chapter 1 from the beginning of the year when we have to describe distributions. And now we're talking about sampling distributions here, so we're going to make a histogram of these sampling distributions. What we just described is a sampling distribution. The sampling distribution of a statistic, like X bar or p hat, is the distribution of values the statistic takes on in all possible samples of the same size from the same population. So what we have here is a sample proportion of proportions. So let's say this question was the percent of people who like cats. And let's say our mean would be around 37%. 37% of people like cats. Now it's probably a lot more than that, but that's what I decided to pick. And what they did here is they found 100 people. That's what our N was. And they asked, how many people like cats? And let's say 35 of them out of 100 said they like cats. So 35% is where we would mark our histogram. Now they did that's for the first time. And then they did it again. And let's say they get 36% of people like cats. And then they did it again. And they did this 1,000 times. If you look on the left side, on the vertical axis, it says a count of 1,000 samples. So they took 100 people 1,000 times to get this wonderful histogram. So let's look at the distribution of the same histogram we were talking about. The shape is symmetric and approximately normal, or we could also, there's a few things we could also call up something approximately normal. I just want you guys to remember that we can also call it bell curved, bell shaped, or unimodal. Remember, bimodal has 2 humps, unimodal only has 1. Unicycle, unibrow, all talk about 1. The center describes the middle, which we're choosing as the median mode, is close to p hat for this sample because we can't really tell what the mean is exactly because we don't have the data, but the histogram looks to appear that the median or mode is around 37%. The spread is the range, which is about 22, the lowest number is 22% up to 53%. Because the distribution is approximately normal, we could use the standard deviation as a measure of spread if we had the actual data, but it looks to be about 0.05. And then there are no apparent outliers or gaps. Remember when we describe these, the acronym I gave you guys to remember is GSOCS, where G represents gaps, S represents shape, O outliers, C was center, and the other S was the other S, which I forgot, spread. Remember, these are the 5 things you want to touch whenever they want you to describe describe a distribution. Whenever you see the word describe the distribution, this is your go-to. This is what you're going to use to describe it. Some cautions in order to be able to describe your data more precisely is check your scale and your axis. Now look, these graphs represent the same data. If you look on the left, the vertical axis has it's going by hundreds, where on the right histogram we're going by 50s, so it looks a lot different compared to the left and the right. Also, the horizontal axis starts at 0.22 and goes to 52%, where the right histogram goes from 0.32 to 0.42, and these are only going by ones, or by 0.01s. Now, if I were looking at the left, I would say the standard deviation is a lot closer because the data looks like it's a lot closer together, where the right histogram looks like the standard deviation would be more spread out, so it'd be a larger standard deviation. But make sure that you know that this is the same data. So we have the same standard deviation, we have the same mean, even though the data looks different. The histograms do show the same data. Bias of a statistic. We talked about bias in terms of experimental design. What would be an example of bias in a sampling method? There's response bias, so based off of who you're sampling or how you're sampling, someone could be biased on how they answer your question. For example, if I asked everyone, do you think Hispanics are loud? And because I'm a Hispanic, you might answer a certain way, especially because I'm your teacher and I don't want you to be negative about my race. So you might be biased in your answer. Remember, we could also be biased in how we sample. We might not represent all the data, everybody that's in the population. But that's not what I'm talking about here when we're talking about bias in a sampling method. Bias can occur even with perfect sampling methods. So everything through the sample was correct. There was no bias in how they sampled their data. A statistic is biased if the mean of the distribution is unequal to the population mean. So let's say I take a sample of 100 women, and I take their heights, and their heights are all around, let's say, 60 inches. But let's say we know the population to be around 66 inches. Well, this sample is biased even though I took a random sample. The way I sampled these 100 women was perfect. But because 60 inches is so far away from 66, it's biased, and that's something we can't control. So then, the mean of a sampling distribution of an unbiased statistic is equal to the true value. Whenever you see true value, we are talking about the parameter being estimated. We also call this unbiased estimator of the parameter, the mean of a sampling distribution. So remember that the mean of a sampling distribution is an unbiased statistic, which is equal to the true parameter of the parameter that we're estimating. Variability of a statistic. This is just the spread of the sampling distribution. How much variation is there in the distribution of my x bars or p hats? How spread out is my histogram? The larger your sample, remember, the more samples you take, or the more people, fish, dogs, whatever you're sampling, the more you have, the less variation you have. It does not matter how big the population is, the sample size is what determines the amount of variation. So let's say, for example, I'm going to make a dot plot of heights. So I have from 57 inches, 58, 59, all the way up to 68 inches, which is around 5'8". I know I could have someone a lot taller than that, but let's say these are high schoolers, high school females. And I take a sample of 5. So I have 1, 2, 3, 4, 5 people. That looks very spread out. Let's say I take another 10 people. So the more people I pick, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's more data. It looks like there's less variation. It's less spread out. If I take another 10, I don't know how many dots I just drew, but as you can see, the more variation I have, the more samples I have, the more people in my sample, the less variation, less spread out it looks, and it looks more full. So think about it. Consider an opinion sample about the president's approval ratings and pretend that the proportion of those who approve in Orlando is the same as the proportion of those who approve in the entire U.S. An SRS of 1,000 adults taken out of Orlando should be just as precise as taking an SRS of 100 adults taken out of the entire U.S. or 1,000 adults out of the entire U.S. because Orlando has the same proportion as the entire U.S. This is really only true as long as your population is much larger than your sample. A rule that we're going to go by, which we kind of learned in our last chapter, was 10. If it's 10 times your sample, if the population is less than 10 times your sample, then you should be good. Here, I want you to see which is which. High variability, remember variability is how spread out your data is. And bias is how much from the center it is. It talks about the center. So if I have high bias, that means I have a lot of bias, which is it's very far from the center. If I have low bias, it's not very far from the center. Variability, if it's very spread out, high variability means it's very spread out. Low variability is not very spread out. So what we're going to do here is we're going to classify these 4 targets as if I'm playing darts to high variability, low variability, or high bias and low bias. All right, so let's classify them. Here, see the dots aren't very spread out as they are here and here. So I'm going to say that this has a low variability. And bias, it's very far from the center. The center is right here, and it's over here. Most of my data is very far off from the center, so I'm going to say that this has high bias. On the bottom left, our data is very spread out. It covers a lot more of the target. So I'm going to say that this has high variability. And the bias, it's pretty centered. It's pretty around where the middle of the target is. So I'm going to say that this has low bias. It's close to where the center of our distribution should be, which is in the middle. On the top right, I have my data very spread out again, just like the bottom left one. So this is going to have high variability. And then we have high bias because its center is really off. The center is supposed to be here, and it's way to the right, top right of my target. So we have high bias. And then the bottom right one, which is what we want to happen, right? If I was playing darts, I want all my data in the middle. When I'm throwing, I want to be consistently throwing in the middle. So I want low bias and I want low variability. That will tell me my parameter as closely as possible if all my data is centered around the same area. All right, and here's your homework, number 1 for sampling distributions. Remember that your homework's going to be due when we take our Chapter 9 test, which won't be until after semester exams, but I suggest you do it to help you prepare for your quiz. Remember that the 9.1 quiz is going to have whether you have to say if something's a parameter or a statistic. And you also have to tell me if you might have to describe a distribution. So think back to the beginning of the year when we were describing the histograms. And then lastly, distribution. We talked about bias. Remember, bias talks about the center, how far away from the center your sampling distribution is from the population, and then variability, how spread out the data is.